Makwana. I'll be presenting NumLin today, which is a DSL library for using linear types for interacting with linear algebra libraries. So NumLin started off as like my master's thesis. It was 2017. I was like, I wanted to use linear types, and I wanted to use it in OCaml. I just seen the Haskell paper that had come out that year. But I wanted to do it as a library so I could use it right now without having to kind of modify the compiler. So as a brief recap for anyone who might be new to this, linear types are kind of just a way of saying tracking resources. So for example, if you use a linear variable, it's no longer in your context. If you're typing a pair, then each component of the pair will use a different set of resources. But quite honestly, linear types are almost an implementation detail for what I'm about to show you. I wanted to explore programming with pointers. This is things like aliasing, memory management, read-write permissions in the context of matrix programming, such as if you have an expression like C equals A times B plus C, this is fairly easy to do if A, B, and C are values, word-sized, integers, doubles, etc. But it's a bit difficult to do if it's a matrix expression. Why is that? Because there are BLAS routines. BLAS is basic linear algebra subprograms or subroutines written in Fortran, highly optimized, which have certain rules for using routines which do computations like these. And this is some kind of Fortran code for that. But it relies on certain assumptions about aliasing, right? So the easy thing to do would be just copy everything. And this is what NumPy, Julia, OWL for OCaml do. They say, well, we don't want to worry about aliasing and all these kind of permissions, so we'll just defensively copy all intermediate expressions. However, if you want to write an optimized routine for yourself, you have kind of two options, which is, well, you can use the ones provided by the library. So NumPy might have a specialized function to do something, or you can write one yourself, but that one will do the intermediate defensive copies. If you want to kind of go break the abstraction level and go one level deeper, you need to keep in mind all of these rules. For example, A and B may alias each other. However, C must not alias either A or B. A and B may be read from but not written to. C may be read from and written to. And this is also assuming no memory overlaps. You can remember the rules if it was like, one routine, one call, one line on the screen like this. But frequently, you're dealing with code which is like this. This is the wall of Fortran, like I call it. So the equations on the top of the screen are for a Kalman filter. And this code is implementing that. So you might be lucky and you might have some useful comments. So there are some comments along the top where we declare the variables and we also see what values that variable stores over time, so to speak. And you also have some kind of helpful imperative style looking code here to maybe make some sense of it. But even this is not ideal. You need to figure out what the temporaries are, where they're being used, what values stored in them. It's kind of reminiscent of programming with assembly and register, and you have to keep track of what's been calculated so far. And of course, you might not even have the helpful comments for this code, so quite frequently you might be dealing with something like this. So this sort of code starts to look a lot more attractive. However, the problem here is the one I mentioned before, which is temporary matrices for operations which you as a programmer know can be reused. Every single binary and unary operation for this code creates a new matrix. So you end up having this dichotomy of safe and easy to reason about code on one side, but this kind of efficient but dangerous C Fortran code on the other side. You also have, in some cases, escape hatches from the NumPy, OWL, Julia world into the other side to let you do the kind of low-level programming, but then you lose all the guarantees that you had in the first place. So NumLin is my idea for sitting between the two worlds. You can get the control you want, but also the safety guarantees. And the way we do this is using linear types. This is a usable library, meaning as a DSL, you can download it right now. You don't need to modify the compiler. Linear algebra, this is stuff like OWL, which is a linear algebra library for OCaml, but it has bindings for BLAS and LAPACK. Matrix expressions means you don't have to use the opaque calls for the Fortran. You can use natural-looking matrix expressions such as A times B plus C. Safety is with respect to aliasing, read-write permissions, and memory management. And explicit means that it's kind of keeping in with the systems programming or OCaml ethos in saying, oh, this is when I allocate memory, this is when I free memory. You can see where things are being reused. So let's start with NumLin syntax. Here's a quick summary of the types and expressions in NumLin. The thing I want to focus the most on is the one at the very top, F, which represents fractional permissions. So we either have a variable, a Z, or f of s. However, Z is actually representing the 0 in 2 to the 0. 0, in this case, that's a whole permission. You have complete ownership of the array. You may modify it, you may free it as you wish. F of s represents, or can be read as half of f, meaning you have half of the permission f. Our types are familiar, units, bool, integers, elements. However, anything which we don't consider a value, such as a pointer to an array or a matrix, is indexed by a fractional permission. We also have the bang modality for being able to use values intuitionistically. So, for example, being able to say x times x when x is an integer. We have pairs and functions as well. Another feature that I want to highlight is in the term level is corresponding to the type level. So this is the constructor or the introduction rule for the bang, and this is the eliminator. This is how we introduce fractional permissions, and this is, abstract over them, and this is how we specialize them. We also have recursion and higher order functions, which is an important aspect of this language. Now, I think the most important contribution of my project is the idea of giving fractional permission linear types to existing linear algebra, BLAS, or LAPACK routines. The one at the top is, if you can understand that, you'll get the gist of the talk, which is you have a matrix with an arbitrary fractional permission, but you only have one alias of that. By sharing it, you have the permissions, however many they may be, to get two aliases to that, but each with half the permission. Now, you can reuse the matrix in different contexts. For example, we'll see one later where we use it for squaring a matrix. Another example is GEM. GEM stands for generic matrix multiplication, and that is exactly the C times A plus B, C equals A times B plus C that we saw earlier. In this case, this is the A parameter, this is the B parameter, Y, and the matrix that you own and modifies is C. The extra things here are for scalars, for alpha A, for example. The Boolean is for transposition of each matrix. And because of the linear style, you must return every single parameter that you consume, especially the ones that you don't have ownership over. We'll come back to this slight inconvenience later. So to explain this maybe in a bit more intuitive context, we'll use some examples. The core idea of NumLin is that you write a program at the top, it gets compiled to OCaml at build time, so to speak, and then you can use it from within OCaml like any other program. So we have at the top a declaration of a function called square. The bang square is to say we'd like to use the square function more than once, which would be great. We have a fraction polymorphic matrix X. So this may be a matrix that can be owned, but it may be one that is shared. We don't know. Therefore, the only thing we can do with it is read it. We get the size of the matrix, and this is the inconvenient rebinding that we see. We get the X back, and we also have bang M and bang N. These are syntactic conveniences to be able to use the integers intuitionistically like we're used to. Then we share the matrix X. So this is how we get two aliases to the same matrix. Now, even if it was a whole permission before, we definitely cannot have a whole permission now. We have two halves, and therefore it is definitely read-only. Then we pass it in to a function which allocates a new matrix, and in that matrix stores the result of multiplying the two arguments. Once we have that answer, we can then say, let's unshare x to recombine the aliases and return it. So this code is actually just translated into OCaml. And there's a direct correspondence between almost each single line and the OCaml that is a result of it. The thing that I want to highlight here is that this is just syntactic convenience for first creating the matrix, like I said, and then calling the gem routine. And here we have the read-only parameter A, read-only parameter B, and this is the temporary matrix C that is written to. This gets around the problem with linearity, which a kind of a problem with linearity, which is you have to keep rebinding arguments that you only read from. We get around this using syntactic sugar, actually, and some desugaring. So the one thing that you saw one of the things that you saw on the last slide was the bang M and bang N kind of syntax. That is just a way of saying this construct in the core language. At this point, X has type, if E1 has type bang T, at this point, X has type T. But it is an intuitionistic T. At this point, this many X has type double bang T. And when we eliminate it, we have an intuitionistic bang T. If that's a little tricky to follow, that is completely okay. Once you see the tools and work it for your rules and work it out for yourself, it will make complete sense, and you'll wonder why this didn't make sense in the first place. One thing we quickly noticed, though, that with the linear style is the constant rebinding of parameters that aren't modified. So we deal with this to have ergonomic algebraic expressions by using some simple pattern matching, actually. So let's take the example of generic matrix multiplication. We may have x1 and x2 as matrices that we only read from but never write to. The only thing we really care about is the matrix being written to and then the new name for that matrix. So we only care about y, so that's what's visible to the programmer. And the rest of the details for rebinding the use parameters are just rebound kind of behind the scenes. You can use the syntax if you want explicitness, but we think that this pattern matching helps keep the code looking nice and tidy. Now I'm going to go through a few more examples with a little bit more pace so we can get through to the more discussion about what this brings you. This is the code for summing an array. We have an index I, a limit or length of the array n, and an accumulating parameter x0. We have a read-only array of elements, and we're returning that array with the sum. If we're at the base case, then that's it, and we can recurse otherwise. Now, this is an example of a recursive function using linear types. We'll explain why we can allow recursion with certain limitations soon. If this doesn't type check, we can also say, hang on, you were trying to do something that I don't think you meant. You were trying to write to an array that you don't necessarily own, or you're trying to free an array that you don't necessarily own. We can do the same thing with a more complex example for linear regression. And we can also do a simple one-dimensional convolution. In this case, I've made a few simplifying assumptions for the sake of the simplicity of the code. But the idea is that you have a read-only array of weights that you can slide over and a write array that you can modify in place for the convolution. All of this is ensured to be safe using the types and the fractional permissions that we mentioned earlier. And now we can come back to the Kalman filter example. The reason that the code on the left is a little bit longer than the mathematical expression on the right, above, is that it's let normalized. Every binary and ternary operation gets its own line. However, it's still quite algebraic, and you can follow the sub-expressions through the data, through the program. And this is translated directly to OCaml code. It need not be OCaml if you only have first-order functions, so like C or Fortran is possible, though we haven't done that. The formal system is based on a typing judgment. We have to keep track of fractional permissions, intuitionistic variables, and linear variables separately. Expressions have a type T. We use value restriction for bang introduction, and this is important to prevent the example on screen from type checking. We also, using these introduction and elimination rules, are able to explain why the desugaring works in a type-safe manner. I'm going to skip over this because I mentioned this before. And we also have rules for specializing and generalizing fractional permissions. We managed to do recursion by ensuring that the recursive function is type-checked with respect to an empty environment, or the environment only including one linear argument. So the recursive function can call itself arbitrary many times, and that's okay because it only uses the linear argument once. We also have a operational semantics for this. This requires the heap and an expression. A heap consists of a location pointing to a matrix with a certain permission. So for example, you can only free a matrix when you have a whole permission for it. Once you have a share, you can half that permission and get 2 aliases, and similarly for unshare. And this is the gem which requires that locations 1 and 2 can have arbitrary fractional permissions, but location 3 must be owned with a whole permission. Soundness is us saying that the type rules, if it type checks, it will go through the program without being stuck. This ensures that read-only aliases are not written to, and we only free a matrix once it's been allocated. We don't do double frees, such and so on. Errors which are very easy with Fortran or C. The implementation is a mapping from NumLin to OCaml types. Because we do the linearity check, we can embed it into OCaml for a kind of sanity check on the polymorphism, and I'm sorry, not the polymorphism, but the constructors. And so we can use it from OCaml like this. And you can just get the linear types within OCaml. We compared the implementation against several examples. One of them was a Kalman filter implemented in C. And we found that for smaller matrices, that actually the reusing memory saved pressure from the garbage collection and made it faster there. Although the time kind of tends to be dominated for larger matrices for the n-cubed matrix operations, you're also getting more matrix, you're also getting more savings in memory as you increase. So we have many things that we could do to extend this, but at this point I will have to take questions. Thank you for listening.
Have you considered using something like borrowing instead of the linear types?
Pardon? Borrowing?
Yes, instead of linear types.
So there's been some recent work, I think the paper's called Rust Distilled, which tries to explain Rust's borrow checker in terms of a simpler fractional permission calculus. So the ideas might actually be quite similar in theory. And also fractional permissions allow trade explicitness for simplicity of implementation. Typically fractions and borrow checking tends to be a more complex system. This is fairly easy to explain and read. You have a question at the, yes?
As I understand it, you got your, you write your linear program
yes.
in a little domain-specific language,
yes.
and then you translate it into OCaml.
Yes.
And then you combine that with the rest of your program
yes.
and let the OCaml compiler do what it wills.
Yes.
So 2 questions. One is, might you, when you're writing the linear part, think, oh, I just want to reach for this feature of OCaml, but it's not in this little linear language. That's one half. And the other is, what would happen if the OCaml compiler did some crazy code motion thing that ended up sort of defeating some of the assumptions about reuse that you'd carefully put in the operational semantics that you proved sound. Mm-hmm. Do you see what I mean? Because who knows what kind of craziness goes on in the OCaml compiler? So, I mean, I hope a lot.
So for the first thing, yes, that can be a thing. Right now, what I would just do is find a feature, or then just add it. Well, typically just primitives.
Okay, good luck with that.
But those tend to be primitive functions rather than actual features of the language. But there's no way to go back, so to speak. But you could have kind of split up your program so you have smaller functions, which does the thing you want. You go back into OCaml, call that again. So it's, yeah. And the other thing about compiler optimizations? No idea.
Yeah.
It could happen.
So it could happen.
But I'm unaware that OCaml will do anything that crazy.
Oh, it can't actually, says Neel. Okay. So tell us why it can't.
The reason it can't is it would break the garbage collector invariance if it did the particularly crazy optimizations.
Okay. I should interrogate you later. Yeah. Right, so it could be.
We have one question at the back.
Thanks for the talk. It's quite interesting. Now, some people say that linear types are no more because we have quantitative typing, and that includes notions of erasability, and that's with the 0 value. Do you think that's something that you could extend your framework have and be able to? Do you think what could you then think of how your reasoning could be improved with in detecting dead code?
I'm so glad you asked this question. I would love to be able to talk about matrix partitioning and being able to own and alias different parts of a matrix. So quantitative type theory would be great for this sort of stuff. We had 2 more questions.
I think we're out of time, so let's thank the speaker again. Actually, let's thank all the speakers of the session.